Now we're going to look at what a lot of people think is the interesting part, which is to start to apply machine learning algorithms to that big data. And although manipulating the big data in and of itself is pretty amazing when you think about the power that you've learned now, which again is to deal with these petabyte-sized data sets or 100 terabyte-sized data sets in an interactive shell, or scripts, but to deal with things feasibly that are enormous. So you've got just for data manipulation a tremendous amount of capability right now already that you didn't have starting out earlier today. But a lot of people, the ultimate end goal with that data is to apply more sophisticated analysis to it than beyond what they want to do themselves with transforms. Although there's an awful lot. I mean, the transforms themselves, you can derive it, you can squeeze an awful lot of interesting data. And there's an awful lot of use cases where that's, all you want to do is really squeeze the data down or prepare it for a pipeline or something else. But let's talk about the, my laser pointer here, about the stuff that, again, for most people is a lot sexier, and that's basically, applying machine learning algorithms now to these big data sets. And tomorrow when we get into deep learning and neural nets, we'll find out that big data is critical just to make those things even work. So you want big data just to get good, effective, reliable results. But if you've got big data, it means you need some way to juggle it well and work with it in a scalable way. You've already learned that. You've learned a basic way to read into big data sets, to juggle and manipulate data. Now let's look at how we can apply to those enormous data sets sitting in memory, apply machine learning algorithms in a parallel way that will work automatically at this large scale and in parallel. MLib is a library that contains most of that stuff that in Spark that we're going to use. It's got, again, nice documentation. So the Apache docs are wonderful, and you're already in that ballpark when you're looking at the Spark documents we were looking at earlier today. So you can find all kinds of great documentation as you do the exercises. I suggest strongly you have this open in your browser next to you. And this is the Python API versions of it for Python. And again, if you're a Java or a Scala person, they've got the equivalent versions there. Let's talk about something that sounds at first trivial and simple, but turns out to be profoundly important to almost all of machine learning and indeed artificial intelligence, which is clustering. I like to start with it because it's trivially intuitive to understand, but people are also dismissive of it and think that it's such a trivial problem. How interesting can it be? How deep can it be in machine learning? And before we're done tomorrow, you're going to have a real appreciation for clustering. But let's at least get started on it now and dive into the capabilities that Spark gives us to do some of these clustering algorithms. So clustering is, well, as the name suggests, pretty straightforward to understand. And as a matter of fact, it's your classic unsupervised learning problem. Like in this case, we have a bunch of coins. We just returned from our vacation in some foreign country where we weren't familiar with the currency. And we came back and we throw the currency on our tabletop. And without us knowing anything about that currency, we can sort it into piles and at least figure out how many denominations we have. So we might not know anything about these coins, but we can at least guess the denomination by sorting them by size and weight. So if we sort our coins by size and weight, we might find some clusters that look like this. And this gives us the beginning to be able to say, okay, again, how many at least denominations are we dealing with without knowing anything else about the data? So this is a typical clustering problem. And when you think about clustering, it leads people to believe then that all problems are as simple as drawing some nice circles around some islands of points. In reality, clustering problems look a lot less like this, a bunch of islands of points, and a lot more like this, a bunch of smeary blobs that are like this. Actually, the reality is most of the time, they're also not two-dimensional. They're in much higher dimensional spaces. And by much higher, I mean hundreds of dimensions, not just 3 or 4 or 5. So clustering is not a trivial problem. But even here, even at 2 dimensions, I mean, if you think writing a clustering algorithm is trivial, do you think that your clustering algorithm would figure out how many clusters there are here? Well, maybe, maybe not. So point being, clustering is not trivial to either write as an algorithm, nor is it trivial to do even with human level intelligence. I'm sure if I asked everybody out there how many clusters there are here, we would have differing answers. And this is only 2 dimensions. But we're going to give ourselves a nice problem to start with. That is 2-dimensional, 5,000 points. So when we're done, we can look at it and see, are we looking at a problem like this or like this or like this? But we're not going to look at the answer till we're done. But just keep in mind that our 5,000 points could be any of these cases or something else we're not even anticipating. So we're going to have 5,000 points, And we're not going to look at the answer first. And you might say, well, why don't you just always graph the data out first before you even attack these problems so you can find the best approach? And the answer is, how do I look at 3 billion points in 22 dimensions? How do I look at that, right? Besides the fact there's a lot of points, how do I graph something out in 22 dimensions so I can start to see how many clusters there are? And you might say, your answer to that might be, well, I don't work in 22 dimensions. I think you're going to very quickly find out as we look at some examples here that the majority of problems are in higher dimensional spaces. The majority of everyday normal scientific problems that are interesting in machine learning or artificial are in higher dimensional spaces. I will explain that comment if that's surprising to you, but most of the time we're working in higher dimensions. So the opportunity to graph something out like this and then decide how we're going to approach the problem is never there. Instead, we're handed the data and it's 22 dimensions and 3 billion points, and somebody says, I need to figure out how many clusters there are for various reasons that we'll talk about. Okay, so let's start out with one that, though, at the end we will be able to graph it, but don't take it for granted you could always do that. Usually you can't. So if you want to follow along, and again, I recommend you do not follow along in real time with me and wait till we're done. If you want to follow along in real time, remember, once again, you should be on a compute node. So if you were on the login node, type interact, get on a compute node, load the Spark module, type PySpark. We're going to be working on a PySpark shell. But again, I recommend you kind of wait till we're done. So let's step through this clustering problem here. So the first thing I did was I load in my 5,000 points you've got sitting around in your clustering directory. And I note that those are a bunch of ASCII text, it's a human readable, nice ASCII text file, which is nice, but it also means that I've got to convert things into a bunch of integers so that I can feed it into my machine learning algorithm next. My Spark machine learning algorithm, reasonably enough, wants a bunch of floating point numbers for its coordinates for these points. And I'm starting out with a bunch of text things. And so this is a good example for us right here of how we have to take scientific data very often and clean it up and transform it into the right format. This is trivial because all we need to do is convert here some strings, which are, so here's what we're starting with. When we read in this text file, we're starting with this. We've got a bunch of pairs of numbers that are actually strings. And what I want to do is I want to split them into two pieces. And we'll step through this here, but I split them into two pieces. So here are my two strings, but they're still strings. And then I want to convert them into two integers. So now I've got the kind of elements that I can feed into a machine learning algorithm. Again, my machine learning algorithm wants a bunch of real integers. It doesn't want an ASCII string up here. So these simple Spark operations right here are trivial, but they're a good example of a real scientific data set where I've got 3 billion points, and some of them are invalid and noisy. Some of them are out of bounds and range. Some of them are missing or corrupted. And that pre-processing of your data is where Spark is particularly wonderful, right? We can, in one simple command, write a filter function that ejects all of our data that's above some bound, right? Another filter that spits out all of our data that's where one element's missing, maybe one coordinate's missing or bad, or corrupted ASCII characters. We can easily filter and clean up our data. And that's no small part of working with a lot of data sets. In our case here, all we need to do is convert them all into integers. So, here's what we've got. We read these things in, and then we split them into two separate numbers and turn them into integers. Now we've got something we can work with. But this is what's happening actually line by line. And again, when I really do this stuff, I do a take here to make sure I'm doing the right thing. Like I hope all of you learned from the first exercise. When you're doing transforms, doesn't hurt to make sure you're on the right track. Take a few, make sure you're doing the right thing. I did that. I was doing the right thing. Now I'm ready to do something interesting, which is to find some clusters. So I load the library, the Emerald library that does clustering. And if you look in the documentation, you'll see there are lots and lots of approaches to clustering. And if not just the Spark documentation, but if you look anywhere, just Google clustering, and you'll see it's a huge and active field. You'll also see that k-means is a very, very popular clustering algorithm. I dare say the most popular for a couple of reasons. One of which is it parallelizes very well, which in this day and age is important. If something doesn't parallelize well, it's not that interesting to a lot of people because they can't use it on big, significant data sets. K-means parallelizes pretty well, works well on GPUs and whatnot. So it's very significant and very popular. So we're going to bring in k-means. And if we look in the document for k-means, it's very nice. It tells us what's going on here. And some of the parameters here make perfect sense, and some of them might surprise us a little bit. So the first parameter here, the RDE that we feed into it, that's great. It wants a bunch of integers, and that's what we're feeding it here with our RDD, a bunch of integers. That's great. The next parameter here is the number of clusters to create. Whoa, wait a minute here. Number of clusters to create, isn't that what clustering is supposed to do for us? Isn't it supposed to tell us how many clusters there are? The problem is that our data is very often this, right? This is what we're dealing with. How many clusters are here is, you might say, a matter of opinion in some sense, right? It's debatable, certainly, right? It's not this. If all of our data looked like this, then our clustering algorithm should very reasonably just tell us how many clusters there are. It should just absolutely spit out every time, every clustering algorithm, there are 9 clusters, no question. But what's the answer here? The answer here is not so obvious. And so clustering algorithms tend, well, in the real world, have to deal with that scenario. And so what our clustering algorithm is going to do is, instead, we tell it how many clusters to create, and it's going to tell us how well it was able to do. And we can monitor that report of how well it was able to do, the cost or its error of how well it was able to do, and try to figure out how many clusters there are. And we can see where the error drops down to some low number. So that's the first thing we're going to dig into. Now, there's a couple other things that's interesting and maybe surprising to people, is that clustering doesn't pretty much just spit back a number of clusters. It basically allows us to investigate and figure out ourselves how many clusters there are. Now, the other thing in here that is surprising to a lot of people is that there is a random seed in here. And you might say, why is there random numbers? Why do we need to worry about initializing a clustering algorithm? What's not deterministic about clustering? Well, once again, when you start talking about a clustering algorithm that's going to deal with complex situations, it basically tries to start assembling clusters by grabbing a point and finding its neighbors. And you might very well find, you will find that the final result might depend on where you started trying to assemble clusters together. You have to make some decision. And how do you make that decision? Well, it's where to start. It's a random number. It's going to tell you where to start. Somebody else starting at a different point, based on a different random flip of the coin, might come up with a different answer. You hope that your result isn't very sensitive to where you start collecting points, because that means your clustering algorithm is having a hard time figuring out what's going on. But you need to verify that. And so clustering algorithms do have a random seed. You might think that is unusual, and you might be slightly uncomfortable with that. We're going to find out that most of machine learning, and certainly deep learning, involves an awful lot of random numbers and random initialization to get things off the ground. That is an uncomfortable and surprising fact to a lot of people to get involved in machine learning, is the vast majority of our useful algorithms are not completely deterministic. They have a random element to it. And that's one of the parameters here that we're going to look at. Okay, so here is what our clustering algorithm is going to actually return to us as we look for different numbers of clusters. We tell it to find 1 cluster and 2 cluster and 3 cluster and report the error. That's the value here, is the error. What is the error? The error is the distance of each point from its assigned cluster. So if we find 20 clusters, it's going to figure out which points are closest to those 20 clusters, and the total distance from those clusters is what it's going to spit out. So for example, if we've got something like this and it says that there are, I don't know, 20 clusters, it's going to say there's a cluster here, and then it's going to find the total distance from all the points nearby to that cluster center. And if that's a real tight cluster, that total error is going to be pretty small, right? The distance from the points from the cluster is going to be small. On the other hand, if it says that, for example, this is 1 cluster here, I think this is probably maybe 3 or 4 clusters. But if it were to say, I think there's 1 cluster centered here, you can see that the error is going to be pretty large, because these points that are far away from the cluster center are going to add up. So the total distance from all the points to their cluster centers is what we're seeing here. That's what this value is right here. And so we can see the more clusters we have, the more the error drops off and gets low. Now you might say, okay, well, that means the best answer is the one with the lowest error. Of course, right? Isn't that what error means? And here's another surprising fact that's generally true in machine learning, and we're going to see tomorrow where it really becomes quite tricky, which is that driving the error to 0 is very often not what we want to do at all. In the case of 5,000 points here, if this was what our data set looks like, and I'm not saying this is our data set, if this was our 5,000 points, and what if we said we want 5,000 clusters? Then our error is going to be 0, right? We put a cluster at every point. Well, that's a nice way to drive the error to 0, but have we learned anything about our data? Does that tell us anything useful to say there's 5,000 clusters with 5,000 points? No, that's ridiculous. That's a silly answer, but we did drive our error to its smallest value. So that tells you that, and we haven't made a mistake in defining our error. You're not going to come up with a more clever error that's going to avoid this problem. Instead, what you're going to find is that driving errors to 0 in machine learning for many different problems and many different algorithms and many different definitions of error is not the final ultimate goal. Instead, you often want to find where the error approaches some reasonable value. In our case, wherever the error seems to drop off and hit that asymptote near zero, that's probably how many reasonable clusters we have. And if we look at this graph for our data, and again, it's not this data set yet, we haven't seen our final data set. If we look at it for our mystery data set here, we can see that right here, right about 15 is where it seems to get very close to zero. And then we can, of course, keep driving it to zero all the way out to 5,000 data points. But I'm guessing that we probably have about 15 clusters here from looking at this last drop off in data. So we keep throwing k-means at our data set and say, find one cluster, find two cluster, find three cluster. And it keeps coming back to us and saying, I did my best job of assembling clusters, but here's what your error is. And I think that it probably did a pretty good job with about 15 clusters. That's my guess. We're gonna have the luxury when we're done here being able to visualize it and see. Let me take a pause here and see if we've got some questions here. If you have a huge data set, sample, oh, well, let's see. There's the sample transformation I talked about earlier is exactly what you want to use. So that's why, and if you look at sample, it's got a lot of options to it because there's a lot of different ways to approach sampling. But sampling from a huge data set is a very common thing to do when it's intractably huge. And there's nice sampling stuff built into Spark. Is the error a least square error? We define the error function. You absolutely, so in this case here, our error is not a least squares error. Our error here is simply the geometric distance to all of the points. There's no point in doing a least square error because we're negative numbers that we want to least square out. We don't. So it's just a geometrical distance point. Is it the only error function we have? No. We could try a least squares error here, for example, if we wanted to. There's lots of things we could do. And in general, in machine learning, you're going to find out you have alternatives, many of which work. And the big debate is which one works best. And we're going to wander into that territory very deeply tomorrow. We're going to find out error functions are a huge part of doing proper machine learning, is coming up with a good error function because there are many alternatives and many of which work, but one of which works best. And then next year, somebody finds one that works even better. So finding an appropriate error function is not a trivial thing. In this case here, we're just going with the straight geometrical distance though, which will work well enough for our purposes. Is derivative error function of finding clusters meaningful? Well, it would be if you're trying to find where the cusp really is. So if we want to quantify this and automate this, and we want to say, where is this last drop off? Then looking at the derivative or the slope of it might actually allow us to find that cusp. So finding a second derivative might actually be even more effective, but we won't dive that deeply into it here. But yes, you could use that if you wanted to find it more automatically. Okay, but in our case here, we're doing clusters manually from 1 to 30 and looking at the graph. And so this is how I generated that graph. So this is the graph we just had. This is what I did. I said, let's try 1 to 30 clusters with k-means. And I kept feeding it the same data set. And I said, do 1 cluster, do 2 clusters, and then print out the cost. And this is actually the data I got out looked like this. And that's what I turned into the graph on the previous slide. So if you run this, you actually get data out that looks like this. And I look on the previous slide and you can kind of see here, it's easier to see on the graph actually, but you can kind of see here where at 15, it dropped down from 10 to the 13th to 10 to the 12th total error here distance. And again, these numbers are just a total distance to each data point these points are all scattered around some 100,000 by 100,000 grid. So that's why these numbers are pretty large. The distances add up a lot over 5,000 points, but the relative values are all we care about. And we can see that there is this kind of drop off right here. It's easier to see in the graph, and that's really where I feel most comfortable finding it. But here are the raw values used to generate that graph. And here's how I generate it. Very, very simple and straightforward for me. But again, this runs in parallel behind the scenes on all the cores, could use GPUs, could do all kinds of fancy stuff that we don't worry about. We're just Spark people, and we just write this stuff out as a simple script. Okay, now I say to myself, as an experienced machine learning person, Spark person, I say, the fact that this thing even has that random number seed, we haven't been entering it here manually, but I know that there's a random number, we're using the default of it. That tells me that maybe, just maybe, this thing depends, it could be sensitive to the random number, to where it's starting to gather points. And if something's really sensitive to random numbers, or if there's even a possibility, I want to investigate. I want to make sure I don't have a fluky answer. I want to see how stable and variable my answer is. So anytime you have a random number involved in any of your algorithms, you want to investigate that a little bit. So here, I'm going to check now between clusters. I think I have 15 clusters. Now I'm going to check between clusters between 12 and 18 here. I'm going to check. And I'm going to do multiple runs and see what my answers look like. So in other words, I just want to do this. I want to do a bunch of runs from 12 to 17. I want to do 10 of these runs from 12 to 17. and let's see where that best answer, that fall off is. And if I do that, sometimes it actually looks like I have 16 clusters instead of 15 or even 17. So it does have a little bit of variability here. So my clustering, it tells me my data is a little bit fuzzy here. It's a little bit entangled, a little bit overlapping. But in general, it looks like 15 is about the best case. So I can see, I've questioned how random this is and how reliable this is. I've investigated a little bit, which you should always do. And I'm starting to be a little bit comfortable with my answer of 15. So I think there are 15 clusters, but we'll find out. But I can investigate and check this stuff very easily and very quickly and interactively in Spark, and again, even with huge data sets. 5,000 data points, again, you might be thinking, I could do this on my laptop, but 500 million data points, yeah, maybe you're not. Okay, now that I've got my clusters, I think I've got 15 clusters, but I want to keep checking. What I really care about are the centers of them. What are the actual clusters? Because in most of the time when you find clusters in a scientific problem, you're interested in then going and applying that information for where are they? If something's growing in a petri dish in clusters, you might care about which samples are growing where or whatever. But so we want to check our clusters. We want to see where our stars are clustered in the sky. We want to see where things are clustered. And so we want the centers of those clusters. And so I'm going to print those out now. I'm going to do those same 10 trial runs here. And now I'm going to print out the coordinates for the center of the good ones. I'm only going to keep the good ones now. So now I added in a little bit of a filter here, a little bit of logic. I said, if the cost is less than this 10 to the 13th, then that's an interesting thing to me. Go ahead and print out the coordinates. So I did 10 runs. I threw out, looks like 8 of them weren't really quite as good. So I took the 2 that were best, and here are my 2 15 cluster centers. And if I look at the centers here, and I'll graph them out, I'd find that they're pretty much the same clusters. So this is a way for me to say, okay, I want to keep checking and make sure I'm not getting lucky or unlucky here. I run 10 tests. I'm running them again between 12 and 16, but now I'm going to be a little bit finicky. Just keep the better results, the smallest number of clusters. Looks like the best clusters. So that's what I'm going to keep. Okay, let's look at what we actually have here. This is our data set. This is the first time we've seen it here. And again, in the real world, we've never even had the luxury of this. We better trust that we know what we're doing to trust our results. But we have the luxury here of seeing this. Our 2-dimensional 5,000 point data set is easy enough to graph. So here's our data set that we've been looking at so far. And you can see that there are some pretty nice clusters here, but it's not trivial to just separate them. What clusters did we find? Let's see those ones that it did report for 15 clusters. And here's what we have. How about that? That's pretty good. I think our clustering algorithm did a pretty good job. And I do believe now that there are maybe 15 clusters here. So we were able, without visualizing our data, to kind of figure out what the clusters were and where they were. I'm pretty happy with this. How about the one that said, say, 16 clusters? Is it just making some random point out here? Is it just flaky? No, this is what 16 clusters look like. Basically, it put a cluster in here. Instead of this being 2 clusters, it said 3. And you know what? I can't entirely dispute that. That might actually, could very well be a cluster, hidden in here. That's the kind of, like I said, fuzziness that's real world data has. So that's 16 clusters. So it's not crazy. It just found an additional cluster right there. So this is what we have right here for our answer. We did a pretty good job. And again, when we go on to data sets we can't visualize, we hope we remember these skills here. We hope we remember there's some randomness to this, but there's some, driving the error to 0 isn't always the answer, et cetera, et cetera. So let's talk about why there might be higher dimensions and why we can't always, why I say this 2-dimensional. Let's look at the actual data, plot it out, and gain some insight doesn't typically work. We're going to find out that the majority of real world problems have more than 2 dimensions. And I don't mean 3 dimensions because we're a 3-dimensional world. I mean like 20 dimensions and 30 dimensions. I'll explain that and motivate that in just a moment here. But if we start out with the idea that our data has a lot of dimensions to it, then getting our dimensionality down and reduced is going to make our problems a lot more workable in several ways, several different but equally important ways. Not just because we can maybe graph things out, which is, again, for our human intuition, makes things a lot more tractable. But we're going to find that a big theme in machine learning, a huge theme, is that our data naturally is going to be in higher dimensions. And again, if you're new to this field, I haven't made a compelling case for this yet, but we're about to find lots and lots of cases where that's true. So our data is naturally just going to be handed to us, going to be highly dimensional. Reducing the dimensionality is going to make the problem a lot easier to work with, both algorithmically and mathematically data-wise, as well as where we can start to derive some real insight into what the data is really telling us. how things are really related to each other. So this whole idea that we can reduce the dimensionality down and it will help us with learning stuff about it is going to be very, very common throughout machine learning. Many different, completely different approaches than this, everything from neural nets to PCA analysis or statistical classical regression, that all of these things could often be viewed most effectively as we're reducing the dimensionality of our data. We're going to return to this. Matter of fact, it's going to come back to us so much in the next, the rest of today and tomorrow. I'm going to put a little badge on a lot of the slides here that whenever we are stumbling into, hey, what we're really doing here with this particular algorithm is we're reducing the dimensionality and trying to bring some data out of that. Okay, now let me though explain why are there all these dimensions, because that's something that's hard for a lot of people to intuitively see up front. Okay, let's take a look at a simple example here from somebody that's trying to characterize you as a consumer. So I picked this because it's nice and intuitive here. So we're, say, Amazon, and you're Amazon and you're trying to figure out who your customers are so that you can either target them with suggestions as to products or send them promotions or whatever. You might start out with something like this. You've got maybe 2,600 categories that you've got available to you. And for Amazon, actually, it would be much, much more than this. But let's say you got 2,600 categories like children's clothing and pet supplies and whatnot. And we keep track of how many purchases any individual makes in that category. So here's a person, and they purchased $800 of children's clothing and $450 of cameras and $350 of containers and no romance books, for example, right? So we characterize a person by their purchases. That seems like a pretty reasonable thing to do. Now, first of all, what we are actually doing from the strictly data structure sense is we have just constructed a vector for this person, a vector here in 2,600 dimensions. Each dimension of that vector has its own value here. So in other words, we can picture this as a 2,900 dimensional space here, where this vector is pointing out to a particular point in that space. Okay, right away, those of you that are new to this might say, what? Now, that's not the only way to think of this. Why would I even want to do that? But bear with me. So we can think of this as we can represent a person by a vector in 2,900 dimensional space that points to a particular point in that space. And the coordinates of that point are given by these purchases right here. So there are 800 units out in the first dimension, 0 units out in this dimension, 450 units out in this dimension, etc. So they're a vector in 2,900 dimensional space. Right away, one thing I might say to you is that if we find that people's vectors, their points in space are very close to each other, that means they're very similar individuals. And that does I hope that makes sense to everybody. If I were to find somebody else who's very close in that space to these coordinates, then that's a very similar person with very similar purchasing patterns, right? So that's one way to look at things. If I were to find somebody that's very far away in that space, I might conclude that they have very different purchasing patterns. So right away, we can just see there's kind of this notion that how close these things are in space, in this 2,900 dimensional space, gives us somewhat of a handle on how similar they are. Okay, maybe you might think, but there's other ways to do that too. But okay, but I hope you at least get the idea that in this 2,900 dimensional space, how close people are, the clusters that they form might be useful. But working in that 2,900 dimensional space would be painful and unintuitive. So let's instead say that we apply our clustering algorithm. We've got this k-means clustering algorithm we've got, right? And we take it and apply it to our data set. So for our 10 million customers in our 2,900 dimensional space, we do our clustering, right? So right away, you can see how we're now in a big data situation and we're in a highly dimensional space. We've got 2,900 dimensions and we got 10 million customers. We're going to cluster them. So we cluster them all. And we find, using this very same techniques that we just used on the previous, our example problem there, we think there are 80 clusters. So we think we have 80 clusters with an acceptable error. We see the error gets pretty low and we get around 80 clusters. So now instead of 2,900 dimensions, we have 80 clusters. We can represent every person by their distance from those 80 clusters. We might find our 80 clusters. We might be able to name them. We might not be able to name them. They might be these abstract things we don't understand exactly what they are. But let's say we go and we investigate, we name them. We can say, these are young parents. This is a college athlete cluster. This is the auto enthusiast cluster. This is the knitter cluster. Then we could take for any given person, and we can say, how far are they from that cluster? If they're very close to that cluster, we might conclude that they're a young parent. If they're very far from that cluster, we might conclude, well, they're not a Shakespeare enthusiast, for example. So now with 80 numbers, we can try to represent this person by their general purchasing characteristics. So in other words, we've reduced the dimensionality of this person from 2,900 down to 80. So we reduced the dimensions, and we've learned something about our customers. We've learned who, we can send different products to because we've seen how they group together. For example, we might have found out that young parents buy not only children's books, but buy a lot of cameras because, people with kids all of a sudden get concerned about security, house cameras, baby cameras, stuff like that, maybe a car camera for the first time. So we now have figured out that young parents also are in the same cluster with a bunch of people buying cameras. But we've reduced everybody. Now we only have to keep track of 80 numbers for every person instead of 2,900. So we're learning something about our data and the universe that we live in, and we're reducing the dimensionality and making it a lot easier for any algorithms to work with this particular person. Okay. There's a possibility point belongs to 2 or more clusters. No, not with K-means. Every point gets assigned to a cluster. Let's see. Are they circles? No, they are not circles. They are central. Let's see. We lose some of the relationships. We don't lose some of the relationships. Well, so reducing dimensionality, and we're going to go into some more examples of this, you'll see, usually is a lossy process. Yes, we're representing you less accurately by these 80 numbers than by the 2,900 numbers. But we hope in the process, we're also learning enough that it's worth the trade-off, and we hope that we're actually losing stuff that's noise and we don't care about to begin with. So we hope we're gaining insight by doing it. We're going to have many more examples of this in many different types of algorithms before we're done. So it is a lossy, almost all of these algorithms in machine learning are lossy, but in a way that we hope actually is useful to us. It's a good kind of lossy, and we'll see it more with some other examples, but but it's already happening here. Let's see. How is the cutoff value for cost determined for clustering analysis? It wasn't a cutoff. We actually manually made an observation of where we saw that cusp in the graph get to 0. So that's how we decided. We said, okay, this is where it took its last plunge towards 0. If you try to be more formal than that, we won't dive too deeply into clustering more, but that's how we did it. We observed it. The cost was the criteria. Yeah. How do I plot the clusters in the data? I used historically over periods of time, I've used a bunch of different things. Honest to God, I think this looks an awful lot like Excel to me at the moment. I think this was Excel. These days, I almost always use Matplotlib for stuff. But for some reason, I think at the time it was at my finger. So this was just Excel. I just took, but again, the data I just took this and I threw this into Excel. But I could throw this into Matplotlib, and you can use Matplotlib within the Python shell right here if you want. So there's lots of ways to plot the stuff, but this is, or this graph here. Yeah, this looks like an Excel graph to me. So yeah, I just took that and stuck it into Excel. So Matplotlib for a lot of you would probably be the most natural way to do it within your Python scripts. Okay, now dimensionality reduction is, I've already given you some reasons why you can see it's a useful and important thing to do. Another reason is one that's there's often lumped under this thing called the curse of dimensionality, and people lump an awful lot of behavior about high dimensional data in here, but really I think people with experience mostly lump things that derive from the phenomenon I'm about to describe under the curse of dimensionality. And that is that geometrical distances become much harder at higher dimensions. And here's how that works. I'll give you the most fundamental example, but the same principle applies to lots and lots of other similar things, which is that if we have a two-dimensional, say, square on the ground, and we throw a couple of darts up in the air and they land randomly, and we look at the distance between any two random points on that two-dimensional graph on the ground. So just picture a 1 meter square thing on the ground. You close your eyes, you throw two dots, through two coins up in the air. You see how far apart they land, right? They're going to land on average about 0.5 meter apart. And you have a bell curve. Sometimes they'll land very close together. Sometimes they'll land near opposite corners, maybe about, be 1.2 meters apart. But in general, they're going to land, not in general, on average, they're going to land about 0.5 meter apart with this kind of distribution. So this is in 2 dimensions. Now let's say in 3 dimensions. Let's say we have a 3-dimensional 1 meter cubed tank, a fish tank with 2 goldfish in it. It's 1 meter cubed. And the goldfish swim around randomly. And at any random time, we take a snapshot and say, how far apart are the goldfish? We're going to find that they're going to have a bell curve distribution like this. Okay, that's fine. They're about 0.6 meters apart from each other on average with this kind of distribution. Okay, that's fine. This is, by the way, just taking random distribution along the dimensions and using Pythagorean theorem. How far apart are they? It's Pythagorean theorem. There's 2 dimensions. X squared plus Y squared, right? This is X squared plus Y squared plus Z squared. Well, we can take that same high school level geometry, and in 10 dimensions, you'll end up with a curve that looks like this. There's nothing fancy about it. It's, we don't need to employ any, higher dimensional geometrical algebra. It's just simply Pythagorean's theorem in 10 dimensions. It's going to generate a bell curve that looks like this. Okay, that's interesting. Well, what's really interesting, we keep following this trend, and we find out that, for example, in 100 dimensions, our bell curve looks like this. It's very peaked. Almost all of the randomly distributed points in our space are about 4 meters apart in 100 dimensions. There's almost none that are, say, 2 meters apart, or 6 meters apart, even though they could be. So what does that tell us? That tells us, well, what does it suggest to us, the trend here? It's showing us that in higher dimensions, our bell curve turns into an outright spike. In other words, all of our random points are about the same distance from each other. That's a very bizarre thing to say, right? Our randomly distributed points are all about the same distance from each other, but it's an irrefutable fact. This is Pythagorean theorem in higher dimensions, nothing more than that, high school level geometry. So this becomes a real issue when you start trying to figure out how far apart are random points. For example, our clustering algorithm is concerned with how far apart are points, which ones are closer to points than others, right? It's trying to figure out how far apart are points from data centers. It has a real time of it in higher dimensions here because everything seems to be about the same distance from everything. And this is the reality. We're just not used to working in higher dimensions. But this is the root of the real curse of dimensionality problems. Again, you'll hear the term used in a lot of cases where it doesn't really apply quite this way. But this geometrical issue manifests itself in a lot of different situations. For example, random vectors pointing in directions in space. In 2 dimensions, if you were to drop 2, say, toothpicks on the floor, on average, they're going to be about 45 degrees from each other, right? In 3 dimensions, if you were to have those toothpicks floating in a tank, they're going to be a little bit more than, a little bit less actually than 45 degrees from each other on average random. Turns out in higher dimensions, almost all of those toothpicks are going to be pretty close to 90 degrees from each other. They're almost going to all seem to be orthogonal. That means direction finding in higher dimensional spaces gets tricky. Lots of other similar things. Again, you can do all these with high school geometry, just taking to higher dimensions. The unit sphere takes almost all no volume in the unit square. It makes sampling very hard. So all of these effects in higher dimensions make working in higher dimensions error prone and very difficult. So it's nice that we can reduce the dimensionality of our data to get away from this as well. It's an important thing. As a matter of fact, metrics, even distances, might not always be as simple as you think. As geometric distances. For example, so far we talked with the data points, we just said, hey, we're using geometric distances. Does that always apply? Well, how about if we were doing chess problems, and you're trying to figure out how far apart things are, then all of a sudden in the chess world, and we'll see how it's not just the chess world, but lots of problems fall into this case. In the chess world, the distance between this point and this point is not Pythagorean theorem. It's, right, we got to take these discrete steps, in which case this distance is the blue line is the same as the red line, which are both a lot longer than the green line, right? So Pythagorean theorem doesn't quite apply anymore if we've got these discrete steps. And you might say, okay, where does that apply outside of chess? Lots of places. Like, for example, if we're comparing strings, we've got discrete distances, steps between strings. As a matter of fact, comparing strings gets us into a territory where it's even very hard to come up with something that actually qualifies as a metric, where actually the triangle inequality, the distance between A and B is always going to be greater than the distance between A to B to C, or less than the distance between A to B to C, right? So, that's not even true for a lot of metrics you can't call them metrics then, but a lot of measures that are useful for things like string processing. And when I say string processing, I don't mean anything particularly abstract. I mean something as simple as a spell checker. Let's say we're doing a spell checker and you want to see if somebody's mistyped a word, right? Something like your phone does for you constantly all day long, right? Well, what should that distance be? Maybe it's the phonetic distance because you didn't know the difference between the word do, D-O, and the word D-U-E, do, right? Those seem like they're close. On the other hand, maybe it's because the keyboard distance, because you accidentally typed the word P instead of an O. They're next to each other on the keyboard. Or maybe it's some alphabetical distance. There's lots of different distances you can come up with, all of which seem like they might be useful in different circumstances. So you can see it's very quickly you can get into areas where distance gets tricky and it's even hard to define. And if you think, okay, well, that's just a unique case of spell checkers, Well, genomic distances, right? Genomes are very important. We're all consumed right now with COVID and vaccines, everything, mRNA vaccines. Looking at genetic sequences is pretty much matching sequence strings between genetic fragments. And they're very much strings in the sense that they are these, characteristic things you represent as strings, as letters, actually, whether, by convention. So at any rate, there's lots of cases where metrics can be tricky. Okay. Let's look at a very classic way of approaching this problem. Let me see if I have some questions here. How do you know you have enough training data that your cluster is giving you meaningful information? It's a very, very good question. How do we know if we have enough data? We're going to wade into those waters tomorrow.